I'm Lindsey, and I'm pleased to be here with Rowan, sharing with you some of the work that we have been doing, deploying a short course on geophysics. And so the course that we're doing, it's called the DISC course. This is the Distinguished Instructor short course. And this is a course that's given by a geophysics society every year. And so what they do is they select one instructor who's an expert in a field and a topic of interest. And they send this instructor around the world to give a one-day short course on this topic. And so this year, my supervisor, Doug Oldenburg, has been chosen to give this. And he's giving a short course on geophysical electromagnetics. And we'll jump into what that is in a second. But some of its applications include things like mineral exploration, or characterizing groundwater, perhaps looking for geothermal reservoirs, or maybe finding unexploded ordnance. All things connected with electrical conductivity and trying to characterize what's going on underground.
So, oh wow. So because this is a diverse audience, I just want to give a quick introduction to what geophysics is. So in geophysics, we're interested in characterizing and imaging the subsurface. So we don't know what's there. And so we might, there's a couple ways to do that. We might want to dig it up, or we could drill it. But another way to do that is through geophysical methods. And so in that, and especially in electromagnetics, you use some sort of source. You could light it up with a battery, or you could use a sort of an electromagnetic pulse to send a signal into the ground. And that signal interacts with the physical properties in there, like electrical conductivity. And then you're collecting data in some way. And so one of the sort of classical applications of electromagnetics, geophysics, is direct current resistivity. So this is basically like using the Earth as a giant resistor. So you're solving the equation V equals IR sort of in 3D using a partial differential equation. And you're measuring potential differences, so the voltages all across the surface. And then you're using those data to reconstruct the image of the physical properties in the subsurface. And so in exploring this, as we would in a course, say, we create a model of the subsurface, and then we need to simulate on that. So we're using some sort of physical simulation tools. We're solving a PDE to get the currents, the charges, the voltages, which are our data in this case. So we're at the Geophysical Inversions Facility, and we've been working at our university as well as a few other universities on a tool called Simpang, and this is sort of our tool that's enabling our research. So there's a lot of things going on here, is like solving PDEs, but also sort of making sure that we can, because in sort of a real life scenario, you don't know what the model is of the Earth. And so you actually need to figure that out somehow. And so you're running forward simulations, figuring out what the data is, and then you're using that data to sort of image the subsurface and get that model. So that involves things like optimization, and that's called an inversion. So we have all sorts of tools available to us, and so those are some of the ingredients that we're coming to when we're going to this course.
And so this course, as I said, it's a one-day short course. And we've developed we'll show you a bit about a textbook that we've been deploying as a part of that. One of the things that we've also been looking to do is leverage a lot of these simulation tools that we've been doing to actually bring the figures to life. And so Jupyter has been an extremely powerful resource for developing and deploying apps in order to enable that. It is a single day course, and so it's a full 8 hours. So one of the essential ingredients is actually having all of that presentation material. And so we have well over 500 slides to make that happen. And so day one is really a lecture style day. And then we're also adding what is a second day. And this is really meant to be more informal, more participatory, and have some discussions. One of the things that I'm excited about that we're doing is actually having participants give presentations. And so by the end of this, we'll have hopefully traveled the world and have an idea of what kind of applications and what kind of problems people are working on worldwide. And so who is actually showing up to this? Who's our audience? So first of all, the participants are primarily industry professionals and some academics. So this is not like we have a captive undergraduate audience. We're not going to be assigning them homework. These are people who have taken a day off of work and are spending money on the course and are hoping to get something useful out of it to apply in their day-to-day work. As I said, we're traveling around the globe. We've got 21 countries that we are planning to go to, half of which we've already done, and by the end, hopefully reaching close to 1,400 people. In order to actually enable the deployment of such a course, we have quite a number of contributors. These are mainly graduate students, as well as a number of academics and collaborators we have outside of our own university. So as we all know here, GitHub is a huge tool for collaboration. So we've used that for some of our work. We got about 16 contributors there, but our actual contributor base in terms of developing content is much wider than that. So we have this opportunity in front of us. What do we hope to actually achieve with this course? So first of all, EM geophysics is actually a fairly underutilized technique. Sorry, EM is electromagnetics. And that is because, you know, electromagnetics gets complicated very quickly. And now we're applying it in 3D and trying to simulate it on the Earth. And so what we're hoping to do first off is show a suite of applications that actually spark some ideas and hopefully engage people and get them asking questions of, can I apply this to the problem that I am working on? If we spark that idea, the next important ingredient is that you actually have a foundation. You have a fundamental understanding of what are some of the basic things I expect to go on. And so that really does actually then set some expectations about what can you hope to gain by adding EM to your geoscience toolbox. The last piece, and this is something that we've seen so much value in the open source world, is actually having a community of people and having a way to interact and engage and continue conversations beyond a one-day course. And so that's something that we would really like to see the development of.
So I think equally in stating goals, it's important to state what are the not goals of this course. And this course is not a course in computation. In fact, there's actually no code that's seen or shown to the people, especially on the first day. On the second day, we do actually get into a few of the, through tutorials and things like that. And because these are industry professionals, we're not doing assessment. There's no pop quiz, so we're not using tools like NBGrader, for example. And we're also not building any infrastructure here. We don't have IT staff, so we're relying on sort of the free and open tools that are already developed. And so I think there's also one distinction that I'd like to make on this on this course specifically, is it's not, again, a course on computation. We're using computation to teach a course. And so there's a lot of really excellent examples out there that are primarily thinking about the code and really teaching with code. In our case, sort of the mode of communication here are the images. So in exploring physics, you want to be able to see the fields and the fluxes and play with that. And so this is what you're trying to interrogate and explore.
And so what are the ingredients here? We have a really interesting opportunity in front of us. There is an instructor and a group of contributors. There's some course material that we have developed and are continuing to develop. We have computational tools, and there is a worldwide audience that we actually have the opportunity to engage with. And so how do we take advantage of this? Before we dive into that, I want to actually look at what is the current model. And so when we were asked to give this course, the second question, once we said yes, is where is the textbook? Where is the Word document that we will print and send to participants? And so typically what would be done is an instructor sits down, they write down things that they know, they use their software tools to generate those images that communicate those concepts. And from there, we go out, we print that book, we give the course, and that is then distributed to the students, and we go from there.
And so if we've done our job right, those students or these professionals want to extend that work, and they want to apply it to sort of a new domain. And so they're going to take maybe their own tools and perhaps create some of their own resources, and then sort of this cycle continues.
And so this diverging development process, it's produced some extremely valuable resources. We have textbooks that we have relied on for years, and that really do capture the knowledge that we need to build upon. But there are some issues with it. There are typos, there are questions about the figures, and how do we interact and update this static medium? And those are only just a couple of the examples, is really, how did they make the figure? What are the set of instructions that reproduce this example that I am looking at? Where's the roadmap? You know, we've fixed a couple of these typos in the errata, and that gets maybe sent out to a handful of people. But now we've got two different versions, and what are all the different versions? Is it just the question order that changed? And collaboration is another thing that is extremely difficult. I mean, everybody's got their own set of tools. We're working on a giant document. How do we actually promote people working together and peer reviewing in a system like that? And so clearly this is a problem. And so this is really symptomatic of this diverging development process that we have going on. You know, we document something to have a conversation, but as soon as we hit print and send that out, that conversation is over. And if you want to continue the discussion, we have to start a brand new conversation. And this is diverging. And so wouldn't it be nice if we could actually iterate in place and think about developing a set of core resources? What if they were tested and we could collaborate on them? What if there was continuous peer review and those updates fed back into the system?
And versioned, reproducible, tested. Like it's open source. so that's sort of the model that we want to take to the development of these educational resources. And really, instead of doing that sort of diverging tree of development, is sort of applying more of that open source philosophy. And so one of the metaphors that is used in software development is the idea of a stack. And Jake Vanderplas in SciPy in 2015 introduced or like depicted the metaphor of the scientific Python stack with Python at the core and sort of like the tools around it, like Jupyter, Python, NumPy, SciPy, and the visualization tools as well. And so what we want to do here is if we're interested in applying that sort of that idea of open source philosophy to the development of educational resources, perhaps like interrogating that metaphor and applying it to what is the educational stack is sort of an exciting place to do that.
And so an important thing to remember is that the stack actually is of no use on its own. It is only when people are interacting with, developing, and using these resources that it actually has value. And so in this case, we're going to have a look at what is the perspective from two of these audiences, from contributors and from participants. And so let's start by thinking about this from the view of the participants. How do we interact? How do we engage with this stack? So if we start at the top, the entry point here really is the course. This includes seeing images in this set of slides, as well as the web-based textbook that we've been developing called EM Geosci. So these images, the text, the context is really the entry point into this stack. So this is how you get introduced. This is where we start the story. And so hopefully, what happens is that you've looked at some of these images, but now you want to ask a question of it. You've been introduced to the ideas, and now you want to go a little further. So we prompt a question, and now we actually need a way to engage with these concepts. We need a way to interact with them. And so what we've been doing here is actually developing and deploying Jupyter notebooks. And this is a way to actually liven up your figures. Have them be something that you can ask questions of. And there's a couple other things that are important at this layer. So case histories, these are really concrete examples of where EM geophysics is being used. It's a little more than just the theory. We want to actually dive into and show examples. That gives you some context and some motivation of real-life applications. What we are calling is apps. And all this really is a combination of some simulation code, matplotlib, IPy widgets, and deploying it with a Jupyter notebook. And so what this does is then it brings to life these figures so that you can ask questions of them. And once you actually are able to ask questions of figures, perhaps the next thing that you want to do is say, how did they go about and create that in the first place? And so in order to enable the interrogation of that question, we've been working on developing tutorials which actually go through and break down step by step how that figure is created. And so what I guess we're trying to achieve here is bringing people down a level further by enabling exploration. Beyond that, what I think something that we can try and aspire to is actually enabling people to extend these ideas to their own work and their own applications. And this is an example that I've been really excited to see have happen out of this. There was a participant in Brisbane recently who took one of the tutorials that we had developed for magnetotellurics. We started with a simple 3-layer model and said, what should the data look like? And then going the other way is how do we actually extract information from those data? And she had built up a synthetic model and actually was having trouble with the black box software that she was using and was able to load that up and interrogate it based on the tutorials. And so I think that this level of engagement and really extension of that work is something that is extremely exciting. And I think that that is really how we try and bring people to this base level, is get something that they can then actually use to answer their own questions.
So I want to take a look sort of from the base looking up, I suppose, of how contributors as researchers were actually enabling some of this. And so we're starting at the base of this. I mentioned sort of a software package that we've been developing called Simpang. And that's sort of done in conjunction with these research papers, research ideas that are sort of this push-pull back and forth between creating sort of a framework that enables the research and the research that pushes back on the framework and the tools that you need to do that. But really, it's one of the things with this set of tools is we want to be able to put that in the hands of other people. And so we've been, again, developing these apps which sort of light up a different part of the electromagnetic application. So direct current resistivity, frequency domain, electromagnetics, magnetotellurics, which are natural source methods, and time domain EM, for example. And so each of these is like a different lens on the software and is getting pushed on by different people. I think one here is it's also important to know that like it needs context. So these apps are not built. They're not sort of immediately explorable. You don't know what questions to ask if you don't have the context of sort of this textbook, all of the slides, all of those pieces around it. And so we've actually, instead of just deploying the Jupyter notebook, we've been exploring Sphinx for documentation. And especially when your course gets to sort of 300 pages or something, having other tools and to cross-reference these things and test them through Travis are quite important.
And one quick thing here to note is that what Sphinx actually allows is that we actually do capture the source code. So those figures that are deployed and shown in the website, they can be tested before we send it off. And the source code is always preserved, so it's not just a static PNG. We haven't lost the instructions.
And so what this is really hinting at is some of the stuff that we heard this morning about reproducible research from Lorena, for example. And so that's really supporting that idea, is now we have a lot of tools out there with continuous integration through Travis CI, for example, to actually push these out into the world. But it needs the people, like that's actually who we're pushing to. And so it's not just enough to make it reproducible, you also need to make it accessible to other people. And so that's where sort of this whole other part of the ecosystem is coming in through binders and sort of the notebooks through Microsoft Azure, as well as Jupyter Hub. And again, read the docs on that side of things as well. And so this is about making those computational tools, those slider bars on our physics, accessible. And yeah, this needs to be in context. So it's in sort of putting these out into the world, it needs an outline. We need to sort of like give people structure of how to approach this. If we're just like throw all of electromagnetics at people, that's way too much. So you need some way to traverse this tree, to cross-reference, to link across to other sites, for example. And it's about, I think another aspect of accessibility is sort of the collaboration side of things. And so how do you collaborate on these resources? And there are new tools that are coming in that make notebooks much easier to sort of work on together through version control, for example. But how we've been doing it, and there was something Lindsey mentioned earlier about the types of contributors that we're going after. They may not know Python, they don't know what a notebook is, and they're comfortable in Word or Google Docs. And so the way that they contribute is through text. And so that's sort of where we've pointed these resources. Yeah, so that's working on sort of reproducibility and then pushing up towards accessibility.
So something I want to bring up here is a bit of a reality check. We have some aspirations to really, bring people all the way through the stack. But there are deadlines to contend with. The course is going on. In fact, it's happening right now. We just got back from Australia a couple weeks ago. And so that we have these examples that we want to deploy and put into the hands of people. We want to have the instructor to be able to open up one of these notebooks apps by clicking a link. By the way, the instructor doesn't know Python, so he needs to be able to click a link, do cell run all, and have physics at his fingertips. We cannot encounter a giant error log. And so what's important to remember when thinking about this is who are the contributors in this case? And they are graduate students. We're not going about this by test-driven development. This is really, for most of these students, I can actually probably safely say all of these students, this is the first time that they've deployed code for the intent that somebody else use it. And so how do we enable this to actually happen? And there's a few levels of asking the question, does it work? And it's important to figure out, where do each of these pieces need to be? And so what that actually means is we need to actually have the organization and the structure in place to actually account for technical debt and to actually have a place where it's okay to have that happen. And we don't want that to be our research code. That's not okay. That's something that we need to be able to rely on, collaborate on, and have as a robust set of tools. But we do need a place where things like the code that runs the apps, sometimes that can be Scratch, and you write a giant script that produces a plot, and that's good enough to get that picture that we need to start communicating the concept, and we can iterate on it later. And so we spent a lot of time actually developing several different repositories, each with their set of expectations being very clear. If this is a research repository, we are going to do peer review. We're going to put in the effort to make sure that it is consistent and styled and tested. But if it is a lower hanging fruit and we need a picture out of it, that's okay too, and there's a different place for that.
So this is sort of like the feedback loop that we're trying to set up is you saw sort of us pushing up this stack, and then we want students to come down and actually contribute back. And so we've really, the start is the reproducibility. Reproducible science is you're taking your software, you have your research, and you can create case histories, but you want to explore that, and that sort of exploration, putting a slider bar on something means that it has to be reproducible. There's no other way to get interactivity without actually sort of dynamically producing these things. And if you're dynamically producing it, it means that it's reproducible. And again, sort of moving up past that second sort of interface is all about accessibility. So just creating those apps aren't necessarily immediately accessible. You need those slides and those other resources like the textbooks to actually make that accessible.
And so the purpose of the course here is we introduce people, first of all, to the concepts and the ideas. And this is delivered by an expert. We are delivering and deploying a course. This is the first introduction for participants to this stack. And from there, what we hope to do is promote and get them to a level where they can ask their own questions. And this is then where the apps, tutorials, and case histories come in, is that this is meant to be something, these are meant to be explorable, something that you can engage with. Beyond that, what we hope to do is actually, if we've done our job and really, if people have comprehended and conceptualized and digested what's gone on, hopefully they are actually then able to take it and extend it and apply it to their own work, do something new with it that was perhaps unexpected. And that actually creates a really exciting opportunity, is if you have been able to extend what has been taught to you, there's actually an opportunity then to contribute back into this cycle, to take that new thing that you've done and feed it back at the base.
So one of the things that you notice here is that we sort of grayed out this reproducibility side of things, and I want to like say that that's not to like sort of discount it or say that it's over or something. Like we are still in that reproducibility crisis, but really, and we should be pushing for reproducibility. But I think by highlighting sort of the extensibility side of things, there's also a way to pull for reproducibility, and sort of like create that feedback loop where you don't have an option to not be reproducible, is you sort of force people through this feedback loop. And so zooming back sort of to the entire ecosystem, realizing that we're sort of in this small part about geophysics, and we didn't want to give a lecture up here about geophysics, so we sort of talked about sort of the philosophies that we're trying to enable and the feedback loops that we're thinking about. And this is really about sort of extending out that idea of the scientific ecosystem to include things like the slides and the textbook. And where Jupyter really has like pushed that ecosystem out by leaps and bounds is seeing all of the interactive apps that are out there and that are displayed in basically every single lecture and talk in this conference. Jupyter has like obliterated that first boundary, and now it's sort of like thinking about like that second boundary is how do we actually bring other parts of the ecosystem into this so that we can like include those in the scientific conversation, so that your first interaction with a textbook, for example, can click source code and then click run and then figure out how to extend that and launch a Jupyter hub and bring you all the way back down so that you're immediately contributing back to the software or to your own research. And really, I think it's what we've had conversations about is like what is tied into this ecosystem. And one place, for example, that we've had problems is actually on the slide side of things. So we have 600 slides that each maybe have 2 or 3 simulation figures on there, but we also want to make it look nice, and there's equations on there, and we want to be able to drag them, resize them, crop them, and that doing that collaboratively under a deadline meant that we were not able to do that in Jupyter, for example. And another place that we're thinking is sort of where are the on-ramps to this system, and like how do we bring people easily through this whole place so that they can get all the way to the base and they can contribute maybe to core Python or core Jupyter.
And so one of the things that comes up there is with the textbook, and we purposefully have tried to keep the text very simple, and so that people can click edit on GitHub and fix a typo, and that can be their first entrance in. And if that is any more complicated than clicking and editing the typo, we're going to lose people, because they're really, the incentive for contributing to this is solely because they see value in it. And if we put too many roadblocks in the way, we're not going to be able to support and facilitate those engagements. And so what we try to do is be very purposeful about the tools and the strategies we're using here. The goal is really to create opportunities and trajectories for people through this stack. Is that if you are introduced through the slides or through the textbook or a case history, that there is a way for you to jump in and engage if you so choose. And in the way we're thinking about that really is, how do we create these feedback loops? Where do you get that feedback? And so in this case, I think the thing that we're trying to emphasize is that there is an emphasis both on the contributor side of things and on the participant side of things. And so what you need to be doing when thinking about choosing these tools is thinking both about reproducibility and extensibility, is how do you facilitate getting your work out, and how do you bring people in? And so I think the question that really excites me here is when you get to the end of a textbook or an exercise, you see, this is left as an exercise to the reader. And what we want to try and do is change that from being, just an exercise to actually being an invitation. That is a way to jump in and learn something new, engage with new content, do something of your own, but also get connected with the community. Yeah.
Cool. Thank you very much.
So the question was asking about, we have a textbook, we have slides, we have code, we have apps. How are you not rewriting everything all the time? And I guess there's a couple ways to answer this. There's some pieces that have been thought about to be reusable from the start. And so there's pieces in the software that easily translate all the way through and have multiple uses. In other cases, what's happening actually is there is duplication, but we try and recognize that quickly. So you duplicate and then refactor. And that's actually part of the chaos strategy that we have, is have a couple places where things can go. And then as we try and bring it down the stack, synthesize and do a better job of both of those instances. So
yeah, I think that's a good question, and that's maybe something that the community should tackle, for example, is if maybe we have this service which just creates that figure and you can deploy to it and then pull that automatically into your slide and just hit the refresh button or rerun or something. It's sort of an open question of how far out do we want our ecosystem to extend, really.
For the most part, it's industry professionals. So these would be practicing geoscientists. In some cases, there are graduate students and academics that come, but yeah, for the most part, it's industry. Perfect. Well, thank you, everyone.
Yeah, thank you very much.